Welcome to video number 355, my dear subscribers and followers. In my earlier videos from 351 to 354, I have discussed properties of time series and identification of time series, and then I also discussed some tools for identification of time series using autocorrelation function and partial autocorrelation function, and then we discussed estimation of the best model among AR, MA or ARMA models, and then we may use that model for forecasting. In this particular video, I'm going to fit a Box-Jenkins model using the simulated data. So I start with the stationary time data, and I'll put it all together using the simulated data. So let us first work with the simulated data, and we will be looking at how MA1 and AR1 series are simulated in Excel and in eViews. So we will learn how to generate MA and AR1 series in Excel and in eViews. And then first of all, using the simulated data, we will view the graph, and we will see how the graph of the simulated data looks like. And we will be viewing autocorrelation function and partial autocorrelation function, and we would consider whether they behave the way as they are expected or not. And then we will be looking at alternative specification, and we will estimate a number of models among which one will be incorrect and one or more would be incorrect, and then we will compare the results. And finally, we may use eViews for automatic ARIMA modeling feature, and we can answer the question whether the correct specification means or not. So since this is a simulated series, so there is no guarantee that the model which we consider as the best works perfectly. So let us start with the simulation of time series data in Excel, and then we will import this data from Excel into eViews. So this is residuals. These are residuals, and these varies from 1 to 500. So there are 500 observations, and this is the simulated YT series, and the division has been given. This is A is the intercept, that is the coefficient of ones, and then this is the coefficient of autoregression, that is 0.7 multiplied by YT with the lagged value, and finally we will add the residuals, and we can simulate, and there are also 500 observations, and this is how we generate MA1 series. So you can see these formulas for yourself. If you click here, here is the formula. Similarly, if you click here, here is the formula for the MA. So what we do, I have already copied this data from observation number 1 up to 500. So there are 500 observations, and you can see that this is quite a big sample. There are 500 observations. I have copied this data from this Excel sheet, and I have copied it here. So this data, basically, first I created a work file, and since this is monthly data, so I use these observations from 1979 month 5 up to 2020 December. So there are 500 observations. So let me show this data to you. First of all, I'll click on this, and here is the spreadsheet of the data. So this data is exactly the same that I simulated in Excel. So I copied that from Excel into the eViews. So first of all, I would like to see its graph, and if you see its graph, this is presumably a stationary. See, there are some oscillations, ups and downs, but it presumably is a stationary series. Then we can also check the parallelogram of this, and we will check this level, and it will include legs up to 36. If I click OK, so here are the autocorrelations and partial autocorrelation and Q statistics. Now if you look at this, regarding the autocorrelation, there is a geometrical decay here, and here regarding partial autocorrelation function, the first partial autocorrelation function is very high, and then there is a sudden cutoff or drop in the partial autocorrelation function. So even if we didn't know that this is AR1 series, we may have concluded that this series behave like AR1. So let us now start it. Let us suppose I go to quick and estimate equation, and y constant and AR1. So this is my estimated equation. So if we look at the coefficient of the AR1, this is more or less the same that we used in Excel. So that one was 0.70 and this one is 0.74. So there is not much difference. And if you look at the significance of this coefficient, the t value is very high and the p value is 0.00. So it passed this test of the AR1. And then we would look at these. See the Akaike information criteria and the Schwarz information criteria. So we will compare this. So let me save this equation. Let me save this equation as I'll save this as I'll save this as y AR1. So this is AR1 series, and now I will check its residual diagnostics and look for the parallelogram of Q statistics with 36 legs, and now this behaves very well, and there is no problem of autocorrelation up to 2 legs. There is some problem of residuals autocorrelation at leg 3, but overall this behaves very well. Secondly, I'll compare this with some other models too. So now let me estimate another equation, y c AR1, and let us add as AR2 and do this. Now if we compare this model with this, the AR1 coefficient is still significant, but the coefficient of the AR2 is not significant, so it didn't pass the test of AR2 coefficient. So this one is okay, but this one is not correct. And we may also compare these statistics, Akaike information criteria and Schwarz information criteria, and seemingly these Akaike information criteria, this value is less than this one. So it means the AR1 this is doing well. So I'll also save this in another name. Let me call it y AR2. So later on I'll compare some other statistics. Now let us suppose I have another model, and I call this MA1. I know that this is not MA1, but I'm estimating this model just for the sake of comparison. So the coefficient is significant for MA1, but this is not correct, because in our simulated data it was 0.7, but this is 0.59, so this is not correct. And thirdly, if we compare Akaike information criterion value and Schwarz information criteria value, these values are higher as compared to these and these. Now I will look at the residual diagnostics and correlogram. Now there are some problems here. Previously in AR1 and in AR2 there was no such problem of residual serial correlation, but in MA1 model there is clearly problems with the residual serial correlation, and similarly there is also problem with the residual partial correlation coefficient up to leg 2. So now let me compare all these models with one another. Now this one is let me check. This one is AR2, and this one is AR1, and where is the MA? Let me check this. This is AR2. So look at these values for Akaike information criteria here and here. Now clearly both the values of Akaike information criteria and Schwarz information criteria, these are less than this, and even these are also less than the other model, that is the MA. So let me check with this one the estimated output, and this is the MA1. So if I compare these, so the Akaike information criteria value and the Schwarz information criteria value are much higher for the MA1. So it means that the AR1 model seems much better as compared to AR2 and MA1 if the diagnostics are correct. So now let me check the diagnostic of the AR1 model. So I'll check the residual histogram. So the residual follows normality based on Jarka-Bera, and then serial correlation that is not available for this model. So I'll also check its transkedasticity, and this is transkedasticity, and I'll be using Bruch-Pagan test. So there are insufficient observation. Anyway, if the diagnostic tests are working well, then the best model would be AR1, and we may use that